So, where does magma actually come from? Now, I know what you're thinking. You've got this one figured out. But trust me, the real story is way more surprising than you'd ever guess. Let's dive in. Okay, so if I were to ask you, how do you make magma? You'd probably say something pretty simple, right? You just heat up a rock, a lot, until it melts. I mean, it makes perfect sense, it's super intuitive, and it also happens to be almost completely wrong. Yeah, I know, that sounds totally nuts. But this idea that you just crank up the heat on rocks to get magma, it's honestly one of the biggest myths in all of geology. And really, this question gets to the heart of the whole mystery. Think about it. We know the Earth's mantle is ridiculously hot, way, way hotter than the temperature rocks melt at on the surface. So, the big question is, why isn't the Earth just a giant molten ball of lava with a little crust floating around on top? What is going on down there that keeps it all solid? All right, let's get into it. It's time to totally bust this myth. We're going to figure out why simply turning up the thermostat doesn't cut it, and we'll uncover the forces that are really at play here, and they're way more interesting. And here it is. This is the absolute key to understanding everything. I want you to remember this. Making magma isn't just about heat. It's a game of physics and chemistry. It's all about changing a rock's environment, specifically its pressure or its chemical makeup. So, okay, how do those conditions actually change? Well, it turns out nature has three main ways of doing it. Let's break down the three big triggers that create pretty much all the magma on our planet. First up is the big one. This is the most common, and you could argue the most important way magma is made: decompression melting. And the name pretty much gives the game away. It's all about taking the pressure off. Okay, so check this out. Deep down in the mantle, you've got rock that is just screaming hot, but it's also under an insane amount of pressure. All that pressure is literally squeezing the atoms together so tightly they're forced to stay in a solid crystal form. But then that rock starts to rise, maybe in a convection current. As it gets closer to the surface, the pressure lets up, and suddenly those super hot, vibrating atoms have room to breathe. They can break their bonds, and poof, they turn to liquid. The rock melts. And notice, it didn't get any hotter. The only thing that changed was the pressure. You've probably seen this happen in your own kitchen. Think about a pressure cooker. Inside, water can be way hotter than its normal boiling point, but it stays liquid because of all that pressure. But what happens the second you release that valve? It instantly erupts into steam, right? The temperature didn't change, but the pressure dropped. That's exactly what's happening deep inside the Earth. So where is this happening on Earth? Well, this is the main engine that creates new crust. It's happening right now along mid-ocean ridges, where tectonic plates are pulling apart, and in places like the East African Rift, where a continent is literally being torn in two. And the stuff it makes? That classic, runny, dark basaltic magma that paves our entire ocean floor. All right, on to trigger number 2. This one is completely different. It's all about chemistry. It's called flux melting. And think of it like adding a secret ingredient, a chemical cheat code that totally changes the melting game. So this happens at subduction zones, where an oceanic plate gets forced down underneath another plate. Now, that sinking plate isn't dry. It's full of water trapped in the rock, kind of like a wet sponge. As it goes deeper, it gets hotter and squeezed, and all that water is forced out. The water then rises up into the super hot mantle rock sitting right above it. And here's the crazy part. The water molecules get in there and mess with the chemical bonds of the mantle rock. They weaken it, which dramatically lowers its melting point. So the rock, which was perfectly solid a second ago, suddenly finds itself way hotter than its new melting temperature. And so it melts. It's the exact same reason we put salt on icy roads in the winter. You're not pouring hot water on the ice, right? You're just adding a chemical, salt, that lowers the freezing point of water. The ice melts even though it's still freezing outside. That's flux melting. The water acts just like the salt. And this is what powers the most famous and explosive volcanoes on the planet, the Ring of Fire. We're talking about places like the Andes Mountains, Japan, Mount St. Helens, all of them. This is where you get those thicker, stickier, gas-filled magmas that build up into those classic, cone-shaped volcanoes we all picture. Okay, finally, we have our third trigger. This one is called heat transfer melting, and it's the least common of the three. But you know what? This is the one time where our original idea, just heat up a rock, is kinda sorta right, but there's a catch. It's actually pretty simple. You've got a batch of super hot magma that came from the mantle, and it rises up and gets trapped inside the much cooler crust. It's basically like putting a red-hot cannonball inside a giant block of ice. The magma just sits there, and all its intense heat seeps out into the surrounding crustal rock, cooking it until that rock gets hot enough to start melting too. Okay, before we tie this all together, there's one last super important detail we have to talk about. It's called partial melting. See, when a rock melts, it doesn't just turn into a puddle all at once. It's way more like a chocolate chip cookie in the microwave. The chocolate chips get all gooey and melt way before the rest of the cookie dough does. And this has huge consequences. Rocks are made of a whole bunch of different minerals, right? And each of those minerals has a different melting point. The ones that are rich in silica melt at lower temperatures, so they turn to liquid first, and this liquid oozes out, leaving the tougher iron and magnesium-rich minerals behind as a solid. This means the new magma has a totally different chemical recipe than the original rock it came from. In fact, this is one of the main reasons our continents are made of lighter, silica-rich rocks like granite. Phew. Okay, I know that was a lot to take in. So let's pull it all together into one simple guide. Think of this as your personal cheat sheet for how magma gets made, no matter where you are on the planet. It really boils down to this. You see a mid-ocean ridge, you know the melting is happening because pressure is dropping, and you're going to get basalt. You're at a subduction zone, that's flux melting. Water is being added to make andesite. And if you have magma cooking the continental crust, that's heat transfer, and you can end up with granite. It's that simple. Setting, trigger, magma type. So look, if there's only one thing you walk away with today, let it be this. Magma doesn't form just because things get hotter. It forms because the rules change. Either the pressure drops, or water gets added, or heat gets transferred. It's all about changing the conditions. And here's maybe a cool way to think about it all. Temperature, that just tells you how much energy the atoms have, how fast they're vibrating. But pressure and water, they're the bouncers at the club. They're the ones who decide if those vibrating atoms are actually allowed to break free and start the party. And that party is magma.